Yes, you are welcome to continuation of our discussions on topics in abstract algebra. I will want to urge you to stay with us as we prove to you in a proposition that symmetric groups are in general not commutative. Although we had some exception that the Kelly-4 group, but in general, symmetric groups are not commutative. I will come with illustration. Okay, so we are going to supply the proof of this proposition that says the cyclic symmetric groups are in general not cyclic. In fact, let me even say not commutative. Commutative, okay? So, proof. As usual, we are going to use the direct proof, okay? Okay, so now let us consider permutations. Okay, let xy be permutations. Okay, in symmetric omega. Okay, a symmetric group omega, such that maybe our x first. Let us say our x is something like alpha beta. Okay, let's use simple permutations. This means alpha is mapped onto beta and beta is mapped back onto alpha. And let y be another permutation, maybe beta gamma. This permutation says beta is mapped onto gamma and gamma is mapped back onto beta. So what is xy then? Xy, the permutations xy will to be alpha beta into beta gamma. So let's see the computations. This first cycle says alpha is mapped onto beta. The second cycle, beta is mapped onto gamma. So ultimately alpha is mapped onto gamma. So I have alpha gamma. Now, what of gamma? Why is gamma is fixed here? Gamma is mapped onto itself in the first cycle, but gamma is mapped back onto, is mapped onto beta in the second cycle. So ultimately gamma is mapped onto beta. So gamma is mapped onto beta. Okay. What of beta? Beta is mapped onto alpha. Beta is mapped onto alpha in the first cycle, but alpha is fixed here in the second cycle. So alpha is fixed in the second cycle. So ultimately beta is mapped onto alpha. So beta is mapped onto alpha. So I close this cycle and let me call this equation 1. So that means my xy gives me a permutation alpha, gamma, beta. Okay. And is what I call equation 1, okay? So let me compute yx, since I'm trying to investigate commutativity. Yx is going to be, my y is beta gamma, and my x is alpha beta. Alpha beta, okay? So the computation is going to be beta, it's mapped onto gamma here in the first cycle, but gamma is fixed in the second cycle. So ultimately beta is mapped onto gamma. So I have beta gamma. Now, gamma is mapped onto beta in the first cycle, and beta is mapped onto alpha in the second cycle. So ultimately, gamma is mapped onto alpha. So gamma, I put alpha here. Now, why is alpha mapped onto? Alpha is mapped onto itself in the first cycle because alpha is fixed in the first cycle. But alpha is mapped onto beta in the second cycle. So alpha ultimately is mapped onto. So alpha is mapped onto beta. So I close this cycle and call this equation 2. Okay. So this means yx is actually a permutation beta, gamma, alpha. And this is what I call equation 2. Now, if you look at it, xy gives me a permutation alpha, gamma, beta. Yx gives me this cycle. Now, beta, gamma, alpha. Now, but clearly, the permutations alpha, gamma, beta is not the same as beta, alpha, gamma, alpha. There are two different permutations because in the first one says alpha is mapped onto gamma. In the second one, alpha is mapped onto beta. In the first one, gamma is mapped onto beta. In the second one, gamma is mapped onto alpha. So there are two different permutations. And since the two are since alpha, gamma, beta is not the same as beta, gamma, alpha, what it implies is that xy is not the same as yx, and therefore this permutation is not commuted. Not commuted. Okay, so I welcome you to the next presentation where we'll continue with permutations.